Good morning to all of you. We are continuing from where we have stopped in the last class, that is yesterday. And yesterday we have discussed about there are about various types of reactors what we have, and all those reactors or the information required for that reactor design can be put in this diagram. That is what I have discussed yesterday. And we have also shown that in this diagram there is heterogeneous system and homogeneous system, and here this is the one which I am going to concentrate. And you can see under kinetics we are discussing about homogeneous reactions only, and not only that, under homogeneous reactions we are also assuming another thing, only isothermal reactors. Okay, now I will start asking these questions now. When we say reactor design, what is that actually we are talking? When you say design of something, when you say about reactor design, then what we mean is that what is the size of the reactor that is required for a given job, and that given job is your input. That means so much you have to produce. So that is why what we have now is the input already with us, and the kinetics. Yesterday I have told you homogeneous kinetics like first order, second order, or some rate equation. It need not be any order. That is also with us. And now we are concentrating on this contacting means the reactors, whether it is batch reactor or continuous reactor. This is what now we have to discuss. And I also want to tell you, yesterday I have shown you so many pictures, and all those pictures, whether it is heterogeneous system or homogeneous system, they can be actually reduced to only these two systems, whether batch system or continuous system. In between we have another system called semi batch, but normally semi batch we don't use unless there is a specific purpose. I am not saying that absolutely no one uses, people use that in industry, but for very specific cases. But most of the time it is the batch reactors and continuous reactors. And in the design when we talk, we are now trying to find out, if you have a batch system, what is this reactor volume, batch reactor volume, how many meter cube or how many liters. Similarly, when we talk about continuous system, we also talk about, yes, now what is the reactor volume when I take a continuous reactor. This is what we have to calculate at the end of the design. I also told you that design is based on, if you have a new reactor, if you want to design a new reactor, then we calculate volume, because you are not having any existing reactor. But in some cases, in one of the industries, they may have already used reactors and they want to use those reactors for a new process. There what we have to do is, you already in the design, you already know the volume of the reactor, but now you know the volume, and you can calculate what is the conversion you are getting from that. That is the one. Okay. So now let me start writing this. Our reactor design is, we have batch system and continuous. Now this batch system means, what we normally do is that we take the reactants at one time, we fill up the reactor with these reactants, and then we will now wait for certain time for the conversion to be achieved. And in the design what we have to do is, you assume that, okay, now I have 90% conversion, I want 90% conversion, then what will be the corresponding volume I have to use. That is what is the design. But you will see later, in batch reactor you will get something else, not directly the volume, that you will see later. In a continuous reactor we have, yeah, this is the one. I think the first one is the batch reactor. This one is the batch reactor. Yeah. So we can see that there is no input and there is no output. We just filled up the entire reactor with the reactants. We close that. Then there will be a temperature sensor, and there will be a pressure gauge to monitor if something is going wrong, and then this stirrer is also put, and many times it is not flat, sometimes you will also have this kind of thing, so that you will have good mixing there. So this is what is the batch system, where you just don't allow the reactants to continuously enter or continuously leave. At one time in the beginning itself, we fill up the reactor with this and then start reaction. And if you want 90% conversion, what you have to do is you have to find out what is the time required for that 90% conversion, right? But now if you already have an existing reactor, and then you can calculate conversion, or otherwise in the design you can assume 90% conversion and then calculate what is the size of this reactor. That you will know when we actually started deriving the equations. In a continuous system, what we do is we take any vessel and then continuously you feed and continuously you can take out the product. So this is a continuous system where you feed all the reactants continuously, product is coming continuously. At this point what you have is the conversion. Now if you have a old reactor already, existing reactor, you don't have to calculate volume of the reactor, but you have to calculate conversion. And when you are designing a new reactor, then you have to fix this conversion at the outlet and then calculate what is the volume that is required for this continuous reactor. Okay, yeah. So continuous reactor. So that is why what you have here is a continuous system. And now in continuous, we can imagine that we can have two types of reactors. In continuous, we have plug flow and we have mixed flow. So what is the meaning of this? Normally what we would like to have is that, someone also was asking yesterday about this question, whether the reactor shape depends on the type of reaction. No. What we are imagining here is what will happen if I take a tube, a tubular reactor, and then allow the reactants continuously to go. I may have even 2 reactors, 3 reactors, they have to be mixed here, and then we will allow them, and then we will find out at this end of the tube what will be the conversion, or in the design you have to calculate the conversion or volume. This is volume, this is conversion, this is input, that is in the output. So that means when you take a continuous system, you can have a very lengthy tube and then introduce the reactants and find out what is the conversion at the end. And the design, you have an equation where you can calculate that also. And there is other extreme where we have a tank reactor where you put a stirrer, continuously you put the input and continuously you get the output, and here the stirring is done. So these are called the tank reactors, and now because you have continuous input and continuous output, that is why it is a continuous system. In fact, even batch reactor also is a tank reactor, but the difference is that there is no input continuously, there is no output continuously. You just put all the reactants and wait for some time and then try to get whatever conversion you want in that volume. That is what is the batch reactor. In continuous reactor, you have in the tank, continuously you have the input, continuously you have the output, and you can again here find out what is the conversion that is required, and to get that conversion, what is the volume required. This is the volume required. Okay. Now you may ask that why can't I use a spherical vessel like this? Or you may ask why can't I have this kind of shape? So theoretically speaking, all these shapes are okay, but in engineering what you have to do is how easily one has to fabricate these units. You know that to make a spherical tank like this, spherical tank, so somewhere here you will have like this, and then when you in the industry in that large scale, it is not that easy to make this spherical tanks. For storage vessels they do if it is absolutely required. Otherwise for reactors mostly the simplest design is this kind of cylindrical tank. Cylindrical tank is just nothing but you join the sheet like this becomes cylinder and close bottom and close top, and you can have of course stirrer and all that the provision. So this is why the fabrication is very easy, that also one has to see. The other extreme is pipes. You would have seen the pipes in your fluid mechanics lab or even in your house when some pumping is done from your well to overhead tank, those pipes we are talking. So those pipes you can just join them, either straight or you can join them, or you can even join them like this. This is input, this is output. So like that you can accommodate now more length if it is really required. So this one is called the tubular reactor, tubular like tubes, and this one called tank reactors. But in chemical engineering we are now defining what is called the ideal reactors. So why this ideality? Why this? What is this ideality? So this ideality, for example, if you take batch reactor, the ideal batch reactor will be a tank with a stirrer, and the stirrer is so efficient that when you are stirring inside this reactor, anywhere inside that reactor, the concentration and temperature is exactly uniform throughout the reactor. Throughout the reactor, the concentration and temperature are uniform. Why? Because if I have different concentrations, then I will have a problem in finding out what is the rate of reaction. You know, in the simplest case, don't take always first order reaction, but as an example always we give first order reaction. In a simplest case I have KCA. Now Ca is, if it is throughout same, then I have only one rate, assuming temperature is same. If I have a temperature here different, concentration different, temperature different, concentration different, then this equation also can be written as Arrhenius equation, e power minus E by RT into Ca. Now you see, temperature also it is changing somewhere, it is not uniform throughout, and concentration also if it is changing, the rate is changing everywhere inside. Here I may have rate, here I may have a rate, here I may have a rate, here I may have a rate. So you have different rates at various points inside the reactor. Now for me to find out what is the average rate to write the material balance is very difficult. That's why what we do is we assume that we have ideal batch reactor. The ideal batch reactor consists of the concentration and temperature at any instant of time. When I look at after starting the reaction in maybe after 30 seconds, at that 30th second, if I freeze throughout the reactor, I have same uniform concentration and uniform temperature. That is the ideality. But we are not far from ideality in a batch reactor. Particularly when you have Newtonian fluids, then it is easy to mix them, and uniformly we can maintain the concentration and also temperature. But the problem comes when you have highly viscous solutions, very highly viscous solutions. Then you will have the mixing may not be proper, then that assumption may not be valid. For that we have to see. That's why in even polymer reactions they will try to dilute with solvents so that the material flows easily. There are many techniques what can be done. So the ideal reactor as far as batch is concerned is that we have concentration and temperature uniform throughout the reactor at any instant of time. At any instant of time. That is what is the ideality what we have. Good. Now once we understand ideal batch reactor, and now we will come to continuous, but before that I would like to ask this question. when you choose batch reactor and when you choose continuous reactor. When do you choose batch reactor? Or when do you choose continuous reactor? Yeah, these are the two questions which we have to answer. So now like batch reactor, that means in the batch reactor there is no continuous input and continuous output. I think I am repeating so many times because at least few of you will catch at some time. Okay, so that is the batch reactor. Now when do I choose that? Normally batch reactor is chosen when I have small quantities to be produced. Small means not the small. I am talking about, let us say, 1 ton per day or 2 tons per day. So if I have that kind of production required, maybe 1 ton, 2 tons, maybe up to 10 tons, right? 10 tons is the maximum. So then you may have batch reactors. But 1 ton, 2 tons and 500 kgs, definitely batch reactor can be used. So that means for small productions, batch reactor can be used, batch. For small productions, here you have to be more careful. Small productions means we are not talking about 1 gram, 2 grams. We are talking about tons, but not 100 tons, 200 tons, 300 tons. But finally, what is the production capacity? Actually, how you have to decide whether it is batch reactor or continuous reactor is depending on, at the end, the finances, right? That means you have to find out the cost of batch reactor. If I am producing, let us say, 100 tons per day, and continuous reactor, the cost of continuous reactor, if I am producing 100 tons per day, and then finally choose. This is the intermediate region. But definitely when they are producing 10,000 tons per day, it is continuous system. Definitely when you are producing half a ton or 1 ton, it is batch system, right? So batch, that is why if you have seen any chemical plant like pharmaceutical and all that, so then you would have seen only batch reactors, because in pharmaceutical industry normally they don't produce 10,000 tons or 5,000 tons per day of a particular drug. So they only produce maybe 1 ton per day or 5 tons per day, like that. So that's why they choose batch system to, because they are producing small quantities. That is one reason. The other reason is that they also should have flexibility in production. Small productions, flexibility in production. Okay, so what is the meaning of flexibility in production? That means today in pharmaceuticals, when I have today you may produce headache tablets. Tomorrow maybe fever increasing in the country. So then you can use the same reactor for fever producing drugs. Or day after tomorrow it may be cold. So that is why that flexibility to change from one product to the other product, that is there in batch system. That is why flexibility in production, if you require, then best thing is to go for batch system. Okay, good. So you have small productions and flexibility. Now the reason based on these two, what are the industries they use batch reactors? The batch reactors industries, normally pharmaceuticals, pharma, drugs, dyes, because in dyes also today you may some people may be interested, many people may be interested in red dyes. Tomorrow, day after tomorrow it may be green dyes, and afterwards it may be blue dyes, all that. Again there is a flexibility in dyes, colors. How do you change the colors? And you also have pesticides, pesticide industry, dye industry, pharmaceutical industry and food industry. These are the industries generally they use batch system. Good? Yeah. So now again I am repeating now. So we have ideal batch reactor as the reactor where at any instant of time the concentration and temperature is uniform throughout the reactor. The reason we are assuming that ideality is to write the material balance very easily, that I will also let you know once more later. Good. So now the question is, when do we use batch reactors? Batch reactors are used normally for small production rates. Small means I cannot give you exactly the boundary. Yes, less than 1 ton you use only batch reactor. Definitely that is acceptable. But less than 10 tons I have doubt. Less than 50 tons I have still doubt. So around 10 ton, 50 ton, 100 tons we have to calculate what is the cost of reactor if you use continuous reactor, what is the cost of reactor if you use batch reactor, and then you decide which one will be the best. Good. So now one drawback with batch system may be that for every batch you may have a kind of every batch you may not keep the quality of the product uniform for batch to batch, right. So we can also see that, for example, our cooking of rice or food industry, cooking of rice is a batch process. So now between batches definitely there will be some small changes of the product quality. Even in industry, when they are using batch systems, there will be slight variation in the product quality. So that is only the drawback in batch reactor. Okay, good. So batch reactor we have learned now what is ideal batch reactor, and we also know when we have to choose batch reactor. Normally if it is 1 ton, 2 tons, definitely we can use batch reactor. But when you are going to intermediate stage like and when you are going to 10,000 tons per day, you don't use batch reactor definitely. But in between one has to find out. And what are the industries? The industries are pharmaceutical industries, dye industries, pesticide industries, and food industries. There may be still 1 or 2 industries. So these people use batch reactors very all the time. Good. So that is the one about batch reactor. We have not yet derived the equations, but we are only just discussing about the difference between batch reactor and continuous reactor. So now when do you choose the continuous reactor? Batch reactor we have just discussed. When do you choose the continuous reactor? Continuous reactor can be chosen, as I told you, for very large production rates. Right? Large means definitely 5,000 tons per day. 5,000 tons per day when you are producing, we will definitely go for continuous reactors. Right? Okay. The continuous reactors again can be classified into 2, as I have already shown. One is a plug flow reactor and mixed flow reactor. Good. That discussion we will postpone a little bit before coming here again comparing between ideal batch system and continuous system. Is there any drawback with continuous system, or is there any advantage with continuous system? We have seen the advantage with batch reactor is flexibility. So I can use that reactor for various products. But in continuous reactor, if you design this reactor for only to produce one product, that is it. You cannot go to any other product unless that product also has exactly the same parameters like temperature, pressure, flow rates. If everything is there, yes. But normally that will not happen in industry. So that is why continuous reactor, once you design for a particular system, for a particular product, that's all. You have to stick to that. But you get in continuous reactor very high quality product. That means always you can maintain that quality all the time. You may operate for 1 year, 2 years, but quality will not change. But what is the disadvantage? The disadvantage is that you have to spend initial investment is very high because it needs a lot of instrumentation because there is continuous flow. So you need flow meters, you need temperature measurements, you need pressure measurements at various points maybe, whereas in batch reactor there is only one measurement of temperature, okay, and there is only one measurement of pressure. There is no flow inside, flow outside. So that's why you don't need any measuring device to flow. I think in fluid mechanics you should have seen the measuring devices like rotometers or mass flow meters or vectorimeters, all these things are flow meters. So those meters we are talking. they are very costly, and in continuous system, that's why that initial investment is slightly high. But you are producing continuously all through, that's why you will definitely get back your money, even though you are able to invest in the beginning more money, right? So that is the difference between batch system and continuous system. Continuous system gives quality, whereas batch system quality variation. Continuous system is more costly and batch system is less costly. And continuous system doesn't have any flexibility, whereas the batch system has the flexibility. So these are the things. Good. So now, when you come to the continuous reactors, as I told you, we have plug flow reactor and we have mixed flow reactor. Yeah, in plug flow reactor is normally the tubular reactor, right? We take a small tube and then continuously entering and continuously leaving. It can be very lengthy also. That's why I am just showing the cut section there. It can be, I told you yesterday, it can be even 1 kilometer length, but that 1 kilometer length is adjusted like this. Okay, good. And in mixed flow, it is a tank reactor. Yeah, that is the tank reactor. So now, between these two, what we have to choose, whether we have to choose mixed flow reactor or whether we have to choose plug flow reactor, this question also has to be answered, right? So now, before answering that, we will define first of all what is plug flow and what is mixed flow. Then we will talk about the other things. So now, when you want to say plug flow, the material is moving inside this reactor, like a plug, like a piston. Like a piston in the cylinder, piston moves like this, and piston, when you have okay, I will just draw here. The piston is like this. This is the piston which is moving in the cylinder. So what we expect is, in a plug flow, this is the kind of profile, velocity profile, what we expect. This is ideal plug flow definition, where we have, I think I will show you. Yeah, so this is the one. You can see this is the ideal plug flow profile. And now please recall your fluid mechanics. When you are recalling your fluid mechanics, when you have a tube and when some fluid is flowing inside, whether gas or liquid, you have what is called laminar flow and we have what is called turbulent flow, right? Yeah. So for laminar flow, the profile will be something like this. That is the velocity profile. For turbulent flow, the profile will be like this. This is for turbulent flow. You can also put the arrows. Yeah. But what we are defining is even beyond these two. What we are defining is this one laminar flow, this is turbulent flow, and if I ask you the Reynolds number, you will tell that this is less than 2100 laminar flow, and here you have turbulent flow can be 20,000, 30,000 like that. But if you go to 100,000, probably you will get something like this. This is very close to plug flow. So this is what we are expecting in plug flow. The ideal definition of plug flow is this, or in other words, the straightforward, I think the correct, necessary and sufficient condition is that by defining this, we have each and every particle, every molecule. Molecule is very difficult to visualize, so that's why we say particles. Each and every particle in plug flow will spend exactly the same residence time. again defining in slightly different way, each and every particle spends exactly the same residence time inside the reactor. That is not possible if I have laminar flow. We know from fluid mechanics, the particle here moves much faster than the particle here. So, the residence time of this is smaller when compared to the residence time of the particle. They are not spending same time. Please recall your fluid mechanics. At the center, you will have the fastest moving particle. At on the surface, you have zero velocity. I mean, we are if you assume no slip condition. So, in between you have residence times of those molecules or particles changing continuously. So, that is why laminar flow is not plug flow. Even in turbulent condition, even here in turbulent condition, so here if I have flat velocity profile, then each and every particle like this or like that, what I have shown, then each and every particle will spend exactly the same residence time if we assume even at the walls you have the same velocity, even at the walls you have the same velocity. So, that is why in reality ideal plug flow never exists, right. But the definition we take as all the particles spending exactly same time, that is a requirement. The requirement for that is a flat velocity profile. So that is the problem now we have in the ideal definition, because this ideality is really ideal. We may not achieve most of the time. I will also give you a simple example like the plug flow. Easiest to remember is if you are standing in a queue, let us say you have gone for a movie, or you would have gone to a temple. So now to see the God, I think when there are a lot of people, they will ask you to be in the queue. So if each and every person in the queue taking exactly same time to see God and then come out, that is what is plug flow, right. So for that, each and every molecule should exactly move the way it moves without any interaction, without any coming back, without any going forward. So that kind of thing, it is not allowed in ideal plug flow, right. So now I will also tell you later why we want to have that kind of restriction, ideality. The reason is again to write a simple mathematical equation. Otherwise, if I take all the variations, the mathematical complications will be very, very complicated. That can be done when you come to MTech or when you are taking slightly advanced reaction engineering course. But here the ideal reactors, and in industry also most of the time based on ideal reactors only it will be discussed, right. In industry, and in industry most of the time they calculate what is the volume required based on the ideal conditions and then take non-idealities into account, right. Okay. So that is why here the ideal plug flow condition will be that each and every particle must spend exactly same time inside the reactor. For that you need this kind of profile. That profile to exist in reality is impossible. You should not have walls at all. And we know that fluid mechanics, when you recall, whenever you have a pipe and then flow, whether it gas or liquid, always we take this no slip condition where the velocity on the surface, inside surface equal to 0, right. So when inside surface the velocity equal to 0, those particles which are sticking to the reactor, it may take infinite time. So that means each and every particle is not spending exactly same time, right. I will give you another example. So now normally nowadays we have a lot of this conveyor belts where you walk, they call escalators. They have, I think, escalators upward and also horizontal escalators are there. You just go and stand there, don't walk, and behind you there is another person who will also just come and stand. Both of you are spending exactly the same time by the time you come the other side. That is what is plug flow. But if someone is moving forward, someone is moving backward, on that then we have what is called axial mixing. So that is what is the next profile. This profile is that some people are coming backward, forward, backward, forward, backward, forward, like that. So that is what is that. That is actually maybe the reality, right. The molecules in a turbulent flow will actually move like that, going forward, going backward and all that. But this information to get is very difficult for us for reactor design. So that is why we assume that this is nothing but a flat velocity profile like this, flat velocity profile like that. So that is what is the meaning of ideal plug flow, right? So okay, so this is the ideality what we have here. But now what can be the non-ideality in this? I think I have forgotten to tell you about the non-idealities in batch reactor. We have only defined ideal batch reactor. What are the non-idealities? Non-ideality simply is no good mixing, right? The opposite of that. And the meaning of that is when I don't have good mixing, then I may have in these corners what is called a dead space. Dead space. Dead space means the material which is there in that corner may not be moving vigorously. That is what is dead space. But in an ideal batch reactor, that kind of dead spots or dead space is not at all available in the reactor. That is what is ideal batch reactor. So that is a non-ideality in the batch reactor. If your stirrer design is not very good, then you will have definitely dead spots here and here. So that is a non-ideal batch reactor. So now for that kind of non-ideal batch reactor, you will not get the conversion what you want in a given volume, right? Okay. So that is why that is the drawback, or that is the non-ideality in the batch reactor. But what can be non-idealities here in the plug flow? Plug flow requires flat velocity profile like this, but in reality you may have this kind of, we call back mixing or axial mixing. Axial mixing. So axial mixing is not allowed to have in the reactor. That is one thing, right? Okay. So the other one is that when the material is entering, you may have the inlet and outlet something like this. If this pipe is slightly bigger, you may connect this with a smaller pipe, where now you have here the dead space. So here also you have the dead space. So these volumes are dead volumes. This is dead volumes. Right? Okay. So now these are not allowed again in a plug flow reactor. Axial mixing is not allowed. That means molecules going forward, again coming back, going forward, again coming back. Again, axial mixing example I can give you is that when you have when you are standing in the queue and when there is a lot of rush, people will be pushing you forward, and you are also angry, and then you are also pushing them backward. So the movement of backward and forward movement is axial mixing. So in ideal plug flow, that is not allowed. So that is why we have now ideal plug flow as only the flat velocity profile, which gives the condition is that each and every particle must spend exactly same time. I started giving the profile first, just so that you are convenient, because profile you know. So with that I have now brought you to the condition that each and every particle must spend exactly same time. But if someone asks you what is the definition of plug flow, what you should say is not flat velocity profile, but what you should say is that yes, in a plug flow each and every particle spends exactly same time. That is the definition. To have that condition, that means each and every particle spending exactly same time, you need flat velocity profile, right? So what we normally write is, to fulfill that condition of every particle spending the same time, the conditions is, one is axial mixing equal to 0. Axial mixing is 0. That is one condition. And then you have number 2 condition is that the radial mixing equal to infinity. Radial mixing is infinity. Infinity is just nothing but at this point when I take, or at this point when I take, at this point when I take, the concentration here, 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 everywhere it is same. When will you have the same concentration? When you have infinite mixing, good mixing. That is what we are also assuming here. If you have very good mixing, then at any point inside the reactor, at any instant, you have the same concentration, same temperature. That is what is the perfect mixing, right? So at any radius, this is the radial direction, this is axial direction. Please remember, this is axial direction, this is radial direction. That's why radial mixing should be infinity. That means here concentration, here concentration, here concentration, everywhere it is same, right? Right, that is radial mixing equal to infinity. That is the meaning of that. Axial mixing equal to 0. That means no particle is allowed to go forward, backward like this. Like people are pushing you forward, people are pushing you backward, and you are moving like this. That is not allowed in ideal plug flow. The reason why we should not allow that is, if I have a molecule which is going here, it is already would have reacted, and then again the same molecule is coming back. There is no use of that molecule because it has already become product. So that is why it will not give you more conversion if molecules are coming backward, forward, backward, forward. Whereas it is converting and then moving, converting and then moving, converting and then moving. At every cross section, you can see that there is some conversion here. Conversion is more, conversion is more, conversion is more. At this point, you have 90% conversion, whatever you decide, or 95% conversion. So that is the reason why axial mixing is bad in a plug flow reactor, in an ideal plug flow reactor. Good? Okay. So now this is what is the ideality in a plug flow reactor. This is what, radial mixing, and of course the third one is dead space should not be there. This dead space normally will not, it will be only in the corners. There is another thing also. If I have channeling also should not be there, channeling. So that means you cannot have only, if I have a tube like this, you have like this only flowing, but all this is not occupied, right? This is channeling. Now when you have packed bed is, okay, I will write here, this is the packed bed. You should have seen in the lab these packed beds. So now you have the flow entering, flow coming out. Yeah. So now if this is going like this, that is channeling. Actually it has to go like this. This is plug flow. All packed beds are plug flow because you can maintain this kind of velocity profile. But on the other hand, if wrongly packing and then most of the liquid or gas is going near the wall, because there you have more easy, no resistance, easy flow. So then it is not ideal packed bed. It is not ideal plug flow. All packed beds are plug flow reactors because you can maintain that flat velocity profile so that you will get for each and every particle exactly the same residence time. So channeling also is not allowed. So these are the things which we should not allow in plug flow assumption. So for plug flow assumption, axial mixing should be 0, radial mixing should be infinity, there is no dead space, no I have to write, yeah, no dead space, and also no channeling. So all these things will be coming, right? So this is what is the plug flow, what in our imagination. See, we say concepts in chemical reactor engineering. This is the concept. Concept means in your mind you are imagining something, you are conceiving some idea. Your idea of plug flow is this, having flat velocity profile. Why? To satisfy that condition that each and every particle must spend exactly same time. You are satisfying that condition. To satisfy that condition, you need flat velocity profile. You should not have axial mixing. Axial mixing must be 0. You should have radial mixing equal to infinity. So these are all the conditions, right? So I think this has to be the definition of plug flow is that the time spent by each and every particle, every molecule is exactly same, right? So when you are writing the material balance, that will reflect. I will also let you know when you are writing the material balance. Okay, good. So that is what is this, about the plug flow reactor. And now we can go to the mixed flow reactor, which is very easy to imagine. Yeah. So mixed flow reactor, yeah, this is the mixed flow reactor. What we normally show, we have a tank and we have a stirrer. Then again, you may also have here something to measure temperature, some pressure to measure, pressure gauge and all that. And then continuously it will enter, material will enter, reactants will enter, products will come out. And here the ideal mixed flow is that again at every point concentration and temperature is same. This is because of perfect mixing. So you should have perfect mixing in the reactor so that the temperature and concentration is uniform throughout the reactor. Right? Okay. So this is very easy to understand, but I think plug flow is slightly difficult to understand. That's why it took more time. And mixed flow is very easy because it is like batch reactor where we have continuous flow here and continuous inflow and continuous outflow here. That is the only difference. But the perfect mixing we also should have here. Okay. Because it is a continuous system here and the material will be falling continuously, you are studying that it is coming out continuously. So people also say that because of this perfect mixing, the concentration here and concentration here inside the reactor and the temperature here and the temperature inside the reactor are also exactly same. What are the advantages of continuous reactor than batch reactor? Oh, that I have already answered, no? Oh, okay. I think the first question I am taking, what are the advantages of continuous reactor and batch reactor? This I have already told you, I think maybe not attentive at that time. So the batch reactors are used only for small scale production and continuous reactors are used for large scale production. Right? And advantage is the quality of the product from a continuous reactor is more when compared to the quality of individual batches. So that means between batches, you have batch 1, batch 2, batch 3 in a day. So all 3 batches, the quality may be slightly vary. Whereas in a continuous system, you have even operate 1 year, you have the same quality. So that is the advantage of continuous reactors, because you can maintain the quality, but only drawback is I am also taking the other one. The drawback between batch and continuous is definitely going to be more costlier, because you are producing large quantities, you can always make up, that is not a problem. And question number 2 is I am not able to understand clearly, what about the resistance of flow impact on reactor flow? What do you mean by resistance of flow? Pressure drop? Yeah. So pressure drop, yeah, the pressure drop will be there in the continuous flow reactors like the plug flow reactor. That has to be taken into account if it is very, very serious. That means if the pressure drop across the reactor is, let us say, 1 atmosphere pressure drop. So then there are ways of taking into the derivation these pressure effects, particularly for gas phase reactions and all that. So resistance for flow will come for gas phase reactions, that is the pressure drop, because pressure and temperature will also give you concentration. Concentration C equal to PA by RT, right? So that's why those things have to be taken for gas phase reactions. For liquid phase reactions, we don't have to take it, but the drawback is that now you should design a pump pressure drop. That's why you calculate pressure drop in pipes. Friction factor you calculate. Why do you calculate friction factor? It is not an exercise that to solve a problem in the class. But actually what you do is, when you are choosing the pump, that pump should have sufficient energy to overcome this friction, the resistance, and then make it flow. So that is the reason why that resistance will automatically come in pumping. That is one thing. But for gas phase and all that, if it is very seriously changing the conversion, we have to also take into account. So things are available there. Okay, I am now continuing the mixed flow reactor. So in mixed flow reactor, we have, as I told you, ideal mixed flow is again having concentration and temperature throughout the reactor uniform. This is called perfect mixed reactor. Perfect mixing. perfect mixing is required. Right? Why perfect mixing is required? Again, at any point of time, I should have the same concentration and temperature so that I can easily find out what is the rate of reaction, because rate of reaction is a function of concentration and temperature. And now even the outlet here, the same concentration and same temperature reflects because of perfect conditions, mixing conditions here. Yeah, perfect mixing conditions here. So that is why we have the same concentration and temperature, and also here same concentration and temperature. In the material balance, I will again let you know how this will really help us in writing the equations. Okay. So all these 9 non-ideal reactors and the definitions of non-ideal reactors is only because we would like to have the design equations as simple as possible. Sir, in which reactor conversion is more in CSTR? Yeah. Okay. I am now coming. I think okay. I am now coming to this drawbacks of mixed flow reactor. We have only told that the perfect mixing is the only one condition for ideality. So what are the non-idealities that can come? So the non-idealities that can come is, again, if the perfect mixing is not there, at this corner you have dead space. Dead space is one of the non-idealities. Good, that is one thing. So now let me also draw slightly bigger picture of the tank. Yeah. So now you have input, we have the reactor. Okay. So now it is stirring. This is coming out. So I think that question you are asking is channeling. Channeling is also a problem. We don't say that one as channeling. We say that one as short circuiting or bypassing or bypass. Channeling is normally used for packed beds and tubular reactors, whereas bypass or short circuiting both are used sometimes in mixed flow reactors. The reason is, if you are not properly mixing it, without mixing inside, this reactant may suddenly come out of this. This is shortcut. This is bypassing. It is not at all spending any time inside the reactor and then going. So that kind of thing is possible in a perfect mixer. So when I have that bypassing is bad, that is bad for us. So we have to now find out exactly what will be that kind of bypassing. And there are ways of finding out in your CRE2 or CRE1, where there is residence time distribution studies and all that. Sorry, I think I can tell you lots of things about this reactor. I can tell, I think, at least 10 hours about these reactors, but we don't have that much time. So that's why I think a lot of explanations I am not able to give. Okay, so dead space and bypass. Bypass is a drawback in a perfect mixer, right? And dead space is a drawback in a perfect mixer. On the other hand, you also have another drawback, that is non-ideality, recirculations. When you badly design the stirrer, very badly designed, and near the impellers, the fluid will be sticking to that and then always moving there only. It won't mix anywhere. It won't go here, it won't go here, it won't go here. Near the impellers only it will be recirculating. Near the impellers it will be recirculating. So recirculation zones are also a drawback, a non-ideality in mixed flow reactors. So I think, I hope you understood what I am trying to say. First we have there are 3 reactors. We have batch reactor. In continuous we have 2 reactors, that is plug flow reactor and mixed flow reactor. And now we have seen the definition of batch reactor as the perfect mixing inside the reactor, and what are the non-idealities that may come. The non-idealities are maybe dead space, and there also you may have recirculation zones, because you are using a stirrer. If the stirrer design is a bad design, then you have a lot of recirculation zone there. Okay, so that is the one. And now coming to plug flow reactor, the plug flow reactor definition is each and every particle must spend exactly the same time. That is the definition. So to fulfill that definition, you need actual, the flat velocity profile. Flat velocity profile you normally don't get at all, because you have the pipes, and near the pipe walls we assume that we have the velocity equal to 0, it is also true that the velocity reduces there. So that is why you never get 100% plug flow anywhere in the, it's only concept in your mind, but you get only in one place. That one place is you have a conveyor belt moving. Over the conveyor belt you now put coal particles. This conveyor belt has pores, perforations. So this conveyor belt is moving. There are holes here, perforations. I send oxygen like this, cross flow. This is moving like this. So the coal enters here, and if there is no disturbance at all, it is smoothly flowing the conveyor belt. Each and every particle here, whether it is side or whether it is center, all the particles spend exactly the same time, and that is a beautiful example of a plug flow. But now this plug flow is now attributed to only solid particles. Each and every solid coal particle is entering here, falling, and then they are simply moving like this. By the time it comes out of the belt, then all the coal particles must have been burnt. That is how what we have to design. So that is an ideal plug flow, because near the walls also there is nothing to stick near the walls. The particles are able to move, and that is one of the very good examples for plug flow. Otherwise, if you take any fluid, either gas or liquid, definitely you will have some kind of low velocity zone. That is what boundary layer and all that near the surface. Okay, so that is what. So that is what we have discussed here. That is ideality, and non-ideality in plug flow is that again axial mixing is a non-ideality. If radial mixing is not perfect, that is also a non-ideality. You may have dead zones in the corners, that is also a non-ideality. And you may have channeling. Channeling means suddenly going through one resistance, least resistance path, to avoid that pressure drop, and then that will come faster. So that will spend less time. So each and every particle there is not spending same time. So these are the drawbacks, non-idealities. And in perfect mixing, the ideal definition of perfect mixing is each and every place in the reactor should have uniform concentration and uniform temperature. But the non-idealities are there, you may have dead space, bypass, recirculation, etc. So this is the concept of ideality. Now, what are the names normally people use for plug flow reactor and mixed flow reactor? Right? So it is not only one name, even though we say I have written only plug flow, but different books also may write these names are different. So plug flow has names like, of course, batch reactor is batch reactor only, you don't have any other name. Plug flow is one name. It is also called piston flow. It is also called ideal tubular reactor, plug flow reactor, piston flow reactor, ideal tubular reactor, and some people also crazily call rod-like flow, Yeah, piston and rod are both are same, but still I think some people say that, right? So these are the general names that are used. I don't know whether I have forgotten one or two things, and these are the general names that are used for plug flow. But in our course, most of the time we call only plug flow reactor. Okay, here in mixed flow, mixed flow is one name, and also we also call this as continuously stirred tank reactor. So we call CSTR. This is widely used. Continuously stirred tank reactor. The problem here is this continuous refers to what? Continuously stirred tank reactor. Even in the batch reactor, we are continuously stirring. Even in the batch reactor, we are continuously stirring. So this continuous should refer to the flow, not with the stirring, right? Because this is a flow reactor. So this is another name, and some people also write this one as C star. C star means C. This is called STR star, continuously stirred tank reactor. So like that, I think this also has any other. One of the old names is back mix reactor. Yeah, some people call this is C star back mix reactor. and called BMR. This is one of the old names. I think nowadays the people are not calling this. It's not fashionable. So that's why you have various names also for these ideal reactors. Good. So now we will derive the equations. We will derive the equations for batch reactor first and then plug flow and also for mixed flow reactors. Yeah, let us take batch reactor derivation. Yeah. So we normally represent batch reactor as like this, and of course, as I told you, here you have a pressure gauge. Here you may have a temperature measurement. Yeah. So this is stirring, and at any instant of time, ideal batch reactor will have concentration, temperature same at any instant of time. Yeah. So just before going to that, writing this, I think I will tell you this is general thing where yeah. So what we write here is for the for deriving the equations is material balance and energy balance. Because we are using only the isothermal system, isothermal reactor, these assumptions are isothermal, ideal batch conditions, and also isothermal system. Isothermal means inside the reactor, anywhere, all the time throughout the reactor, you have the same temperature. So how do we maintain that? It is normally difficult to maintain, but our imagination is that we will put a jacket here, and this is cooling water if it is exothermic reaction, or if it is endothermic reaction, this is a hot fluid where you can maintain the temperatures at that isothermal condition of 100 degrees or 150 degrees centigrade. Okay. So these two are the assumptions. And now you can look at the PPT where we have the rate of reactants into the reaction volume or reactor volume and or an element of volume. So like that you have input, output, reaction and accumulation. These are the terms. And similarly for it is also same for even energy balance. I am not doing energy balance because I am just only teaching only the isothermal reactors, homogeneous isothermal reactors. So that's why I just want to tell you that this is the approach. So we have to find out how much energy is entering, how much energy is leaving, how much energy is carried by the stream, and what is the accumulation, all that. Similarly, mass entering, mass leaving, and also accumulation, and if there is change by reaction, etc. Right? So these are the general expressions what we have. So now let me write that general expression, right. So I am now simplifying that. This will be input. Yeah, let me also assume that I have, it can be written for anything. I am simply writing this. Input equal to output plus reaction plus accumulation. Right. And batch reactor is inherently an unsteady state reactor. So that means there will be accumulation always. So that means the change is with time continuously inside the reactor. So when I put at time t equal to 0 and observe after 1 minute, you will have some conversion. After 2 minutes, some other conversion. After 3 minutes, some other conversion increasing. So like that, it is a transient, steady state, unsteady state process, and this is reflecting in terms of this accumulation term. So we know that because this is a batch reactor, this is only for coolant, not for if it is exothermic reaction. Otherwise, it is hot fluid. So this is only outside the jacket. There is no input, there is no output in batch reactor. So input equal to 0 and output equal to 0. And I also have this A going to R giving me a rate minus RA, where minus RA is expressed like what I have told yesterday, moles of A converted per unit time per unit volume. So when this is 0, this is 0. Now due to reaction, yeah. So yeah, I also have to say that this entire volume is V. V. Now, so this reaction term, we are only writing the mole balance. I think I will also here moles per time. Moles entering, moles leaving, moles reacting, and moles accumulating. So because it is a batch reactor, the moles equal to 0 here, moles equal to 0 here. Yeah, moles equal to 0 here, moles equal to 0 here. Now the reaction term will be, we have reaction term minus RA into V. This minus RA has units of moles of A per unit volume. Maybe later I will write here, per time, per minute. So now this volume is liters. So this will get cancelled. I have moles per minute. So that is what is moles per time, moles per minute. So this is for reaction. So I have here minus RA into V. The derivations are simple anyway. So the accumulation term will have simply dNA by dt. So that means how the molecules are changing with time, how the number of moles of A are changing with time. So that is what is dNA by dt. So when I substitute here, so this is 0 equal to 0 plus minus RA into V plus dNA by dt. Now I have minus dNA by dt equal to minus RA into V. So this is the equation, but this also can be written, we can integrate. But now the conversion in chemical reaction engineering is defined as conversion XA. XA is defined as Na naught minus Na by Na naught, where Na naught is the initial moles you have taken, Na is moles at any time t. Here also I have to write t, right? And most of the time we don't write that, but anyway, that is the meaning there. So Na naught minus Na by Na naught is Xa. That means this is the moles reacted by initial moles. So that is the conversion. So now this dNA by dt, I can now differentiate this. So dXA by dt equal to, yeah. So here I have minus dNA by dt 1 by Na naught. So if I write, this one is equation 1, this is equation 2, equation 3, equation 4, equation 5, equation 6, equation 7. Right. Now substituting this dNA by dt, this minus dNA by dt as Na naught dXA by dt. So this is equation 8. Now substitute this here. So this is Na naught dXA by dt equal to minus RA into V. Yeah. So now this can be integrated. This equation, this is equation number 9. That can be equated. Yeah. This equation. So when it is, you can also write this dt integration this is Na naught, which is a constant, dXA by minus RA into V. So this is 0 to t, correspondingly 0 to XA. So this is the differential equation what we have. integral equation, and after integration you get T equal to Na naught 0 to xa dxa by minus Ra into V. So this is the equation. So this equation number may be 10, this is 11. Actually, this is the design expression for batch reactor. That is the design equation. So that means you have now, if you know the kinetics minus Ra, and here there is some simplification called if I have a constant volume batch reactor. What do you mean by constant volume batch reactor? I will take a steel reactor, the volume cannot expand, it only can break if the pressure is very high. So under those conditions only this V is constant that can be taken out. So Na naught by V will be Ca naught, that is the concentration definition, right? Okay. So but in general this is what we simply leave it here. So I think here I have to talk about, so this is what I am telling, everything is connected, and this volume can be expanding for gas phase reactions, particularly if you have a variable volume. Like let us say that you are conducting the reaction, a gas phase reaction in a balloon. Balloon is very easy for us to imagine. You fill up the balloon, right? So once you fill up the balloon, you start the reaction. Particularly when I have 1 mole of A going to 4 moles of R. So 1 mole of A, stoichiometric equation wise, it is giving 4 moles of R. We know that 1 mole occupies a volume corresponding to that STP 22.4 liters of volume. So depending on the temperature and pressure, always we can calculate that, right? So that means during the reaction, when 1 mole is going to 4 moles, at the end of the reaction the volume should have increased 4 times if the same temperature is maintained and pressure also maintained, right? So that means the volume of this balloon will be expanding. The volume of the balloon will be expanding. So that expanding volume will be normally the Levenspiel has told that can be taken as V equal to V naught 1 plus epsilon A xa. This is how the volume expands, and here this volume is this where epsilon A is defined as volume at conversion 1 xa equal to 1 minus volume xa equal to 0 divided by volume at xa equal to 0. I also have a nice derivation for this, but I don't know, I think I don't have time to do that. So that is why please accept this, otherwise I think you can kindly ask your teachers. So this is the definition of this volume expansion. Volume expansion normally comes only for gas phase reactions where A going to 4R. If I have like this, A going to R, 1 mole is giving 1 mole, there is no volume expansion, right? So it is the same volume. So that is the reason why whenever you have, depending on the stoichiometric equation, we have this epsilon coming into picture where this V is defined like this. This V is the volume, this V is defined like this. So but actually this is for isothermal conditions only, we are designing only isothermal. If it is non-isothermal and also if the pressure is changing, so then we can also derive that equation. That equation I have, but unfortunately I may not have time to derive all that. Okay. So this is the design expression for the batch reactor. Now we also have to do something else here, that is, can we represent this in the form of a graph? Because most of the time this this actually should be integrable. Okay, for constant density T equal to Na naught by V can be taken outside, 0 to xa dxa by minus Ra, and now this is nothing but T equal to C naught This is the definition of concentration, Ca naught. Ca naught integral 0 to xa dxa by minus Ra. So this is the for constant density systems. Okay, good. So now let me plot this equation. Okay. So when you plot this, I will plot this one as xa, this one as 1 by minus Ra. Or I am plotting this, it will be actually minus Ra into V. Okay, that V I will put here. Okay, so that is the one. So now this tells me that this is something like this, a curve where this area, this is the final conversion what I want from my reactor. So this will be the volume of the time T, because that is this integral T by Na naught, yeah, because Na naught I am bringing here. This is the integral I am just plotting here. This is what you have learnt from your calculus and all that. So why we have to plot like this is sometimes this rate is so complicated, you have to go for graphical evaluation sometimes. So that is the reason why we have to plot like this and then get. So similarly this also you can plot, right. So now you have to plot 1 by minus Ra, no V there, and then simply Xa. Now this area under the curve will be T by Ca naught. So this is what is a batch reactor design expression, and in the also in the form of graphical representation. Good. So that is what is the batch reactor design expression. This is what I was asking you. What we require in a batch reactor is the volume. At the end you have to calculate whether the volume is 2 meter cubed or 1 meter cubed or 5 meter cubed, whatever, right. But what you are getting here is only time. And now we have to convert this time into volume. How do you do that? This time is reaction time. And you know, when you are operating a batch reactor, first you have to put. So now the total time required for a batch, per batch, the time required we have to calculate. How do you calculate now? Per batch time, T batch is T reaction time. What is the actual reaction time plus T for filling up the batch reactor, because someone has to start the pump and start the filling up, and you have to fill up till certain level, maybe 2 meter cubed or 1 meter cubed volume, and then that takes some time. And after the reaction is over, then the volume has to be discharged. The volume of this reaction mixture has to be discharged. So that is discharge time. Discharge plus you also have time required for cleaning, if you want to clean that, because you may be going for some other product next time. So now that cleaning time also is calculated, plus we can also have, if it is biochemical reactor is exactly same as what we are talking here. So those students who are in biochemical engineering, they can also believe all this, that this information is required for biochemical reactor design. Okay. So then biochemical people also use for this one as sterilization plus sterilization. So all these timings are required. To give you an idea, let us say that this is 30 minutes. Yeah, this is 30 minutes reaction time, 10 minutes for discharging, 10 minutes for cleaning, charging, discharging both. Okay. I will write here charging, discharging both, charging, discharging. So that is for 10 minutes, and cleaning 10 minutes and sterilization 10 minutes. So totally it is 60 minutes or 1 hour, 1 hour time. So you can make one batch in 1 hour time. So like that you can make, let us say you have 24 batches in a day, 24 batches in a day, right. So because one batch is 1 hour, if you are continuously producing in throughout the day 24 hours, 24 batches you can produce. So now you have to produce, let us say 24 tons per day as an example, 24 tons per day, right, 24 tons and 1 hour per batch. So that means for per batch you have to use 1 ton material. Now if you know the volume, the density of this 1 ton reaction mixture, if the density let us say 1000 kgs per meter cube, that is the density of water, what I am telling, right. So if you know that, you can calculate volume of the reactor. So now you see, once you calculate from this integration what is the time required, that time I am saying it is 30 minutes. So now for all other things you have another 30 minutes, so 1 hour. 1 hour is the batch. So now you can produce 24 batches in a day. For easy calculation, I am assuming now that I have to produce 24 tons per day. So for each batch it is 1 ton. Now this 1 ton reaction mixture I have to put to get the product. So now what is the density of this reaction mixture? Mass I know 1 ton. If I know density, I can calculate the volume of the reactor. That is how you calculate volume of the reactor. Otherwise, you will not get directly volume of the reactor inside the in the reactor design expression. Okay, good. But now I think if you have questions, I think we will spend some time for answering questions. Okay, yeah. Yeah, okay. I think I am ready now to answer the questions.
When we fix everything for ideal conditions, is it correct to use the ideal condition result for non-ideal solutions?
No, if you cannot use. If you deliberately know that it is non-ideal, we cannot use, right? And how to take non-ideal conditions into account will be in the chemical reaction engineering 2. Right? Right now we are only discussing about homogeneous ideal reactors.
So
right?
then why is that we are doing ideal conditions?
Ideal condition gives you the one of the extremes where with minimum mathematics how do you get the volume. Like what reactor you are talking, it is very easy to get ideal conditions for batch reactor. It is very easy to get ideal conditions for plug flow for mixed flow reactor. But only problem is with plug flow reactor it is not that easy. Right? Yeah. So for other 2 reactors, the ideal solutions will give you all the information you require for the design. But for slightly non-ideal factor, if you have plug flow reactor, that only how to take care of and all that we can discuss in the chemical reaction engineering 2. There are techniques. Please don't think that these ideal solutions are not at all useful, because ideal solutions only are the first approximation, and the ideal conditions we can maintain in this batch reactor and mixed flow reactor. So that's why we calculate volume. I will also tell you another thing. Most of the time in industry, we calculate the ideal volume and then add up what is called factor of safety. If the ideal volume what you get is only 1 meter cube, we will say that because it is not ideal, we will add to 1.5 meter cube, another 0.5 meter cube we add, but that is not scientific solution, but it is an engineering solution, because engineering is an approximation of science. Right? Yeah, your question is good, because you can take care of non-idealities at a higher level, but to understand that it is like you have to go through LKG to come to BTech. Right? I mean, you have to start at low level and then slowly build up and then go to complications. So that is why these ideal solutions first we have to do, that too homogeneous we have to do. Then you go to heterogeneous and all that. So TK amma. Is the drying time of reactor is also included in total batch time? Yeah, yeah, it has to be included. Drying time means I think after cleaning and all that, you have to also give some time for drying, right? Yeah, that has to be taken into account. All the timings, what we are losing, we have to add up to reaction time. That is definite. Okay. Is there any way to avoid or overcome bypass? Yes. Yeah. By properly pacing, I think the bypass, particularly we talked about bypass in mixed flow reactors. One way to do that is, so for mixed flow to avoid bypass is, okay, normally we are putting on the top and then taking it out. So this is the one. So stirring. So now don't introduce there, but introduce here. And this is the overflow. So when the input is at the bottom and output is there, at least it has to go through this. This is the shortest distance. So it may go like this, it may go like, because of the perfect mixing, it may go all that. So to avoid bypass, you can change the inlet and outlet conditions in a proper way. Okay, that is good. I think good question. Yeah. Okay. I think that is okay. Can we design a reactor without our minimum dead space? Yeah, it is very simple, because the dead space comes because of improper mixing. If your fluid mechanics are good and if you are able to design a very efficient impeller, then your job is done. So we can avoid definitely dead space, no problem at all. Does the condition of ideality for conduction of biochemical reactors remain same or not? Yeah, even biochemical reactions, you see, I want to tell you the same design expression what we have derived for, yeah, this is the design expression I have derived, right? Yeah, this is the design expression. The difference between biochemical reactor and this normal chemical reactor is nothing except that this minus Ra is the rate expression for microorganisms. So now this minus Ra is not a chemical reaction like first order K into Ca, but this may be Monod's equation or Michaelis-Menten equation or Michaelis-Menten equation modified with something, or Monod's equation modified with there are many modifications required for that. So that is what this minus Ra. So exactly the same biochemical the chemical reactor equations can also be used for biochemical reactors. I think, thank you for asking that question, because there is no difference as far as reactor design is concerned with either biochemical reactor or chemical reactor. Both are exactly same, except that minus Ra you have to use biochemical reaction rate, whereas in normal reactors, chemical reactors, we have to use chemical reaction rate. That's it. That is only the difference. Okay, thank you. Yeah, very good question. For plug flow reactors can be used mostly for gas phase reactions, because high velocities we can use, and the molecules are individually moving and then just flowing. So and also the important thing there is the plug flow reactors, that is tomorrow I think with the derivation that will come, the time required for reaction is very small for a gas phase reaction, particularly for gas phase reactions. Sometimes it is in seconds, sometimes it is in maybe 30 seconds, 40 seconds or 1 minute, 2 minutes maximum. To provide this much residence time in a plug flow reactor, it is easy for batch reactors, sorry, for plug flow reactors. The reason is, I told you, fluid mechanics, right? So when do you get actually, I think, sorry, you actually get plug flow, real plug flow, that is this kind of velocity profile. I have shown you for laminar flow, you get this kind of parabolic velocity profile, right? Yeah. And when you have Reynolds numbers something like 20,000 or so, then you may have this kind of profile. But still it is not flat profile. To go to flat profile, you need almost infinite Reynolds numbers. When you have infinite velocity, very high velocity, the residence time inside plug flow is very small. So that is why you have to put 5 kilometers, 10 kilometers like that. And when you have the reaction going on only for gas phase reactions within seconds, that is very easy to provide this time in the plug flow reactors. That is why plug flow reactors can be widely used for gas phase reactions or even liquid phase reactions where the time of reaction is very small. We don't differentiate either gas or liquid. So whenever you have very fast rates or the time required for conversion is very small for fast rates normally, then we use plug flow reactors. That is very good. Good. I think that is very good question. Thank you. TKM.
So my question is, how can we ensure better mixing with tubes or tanks, especially when reactants in slurry form are used?
Yeah, slurry, see, we are talking about homogeneous reaction right now, right? Okay, when you have the slurries, so that means it is no more homogeneous reaction. You have what is called heterogeneous reaction, and that part I have not covered. And for heterogeneous reactions, the procedure is same, the same reactor design expression, right? And even for slurries, there are very good impellers where good mixing can be provided. You have lots of designs for impellers or the mixers, lots of designs. So for slurries also you may have 1% particles, 10% particles, 30 is too much. So depending on various percentage of particles in the slurry, we have good mixers that can be used.
And then our assumption is that that radial mixing, we are assuming radial mixing to be infinity. So in real situations, there may be actual mixing also. So how can we control that only radial mixing is taking place and there is no actual mixing?
Right?
Plug flow
Yeah.
reactor.
Yeah. So normally plug flow reactors are never used for slurry reactions. Most of the time it is only tank reactors where you can mix.
Can you see any advantage of using plug flow in any field, when compared to mixed tank reactor?
Oh yeah, I answered also one question. For all gas phase reactions, plug flow is the best. All gas phase reactions. Because the gas phase reactions are very fast, you can provide that residence time in a plug flow reactor at high velocities where axial mixing can be almost 0 and radial mixing can be infinity. Good radial mixing can be there for gas phase reactions.
Then also when we can say it is a perfect mixing only if there exists axial mixing also. So if the reaction to be complete, there should be axial mixing, right? So if only radial mixing exists in plug flow, can we say that reaction is complete?
Can we say reaction is complete?
I mean, it is efficient.
Yeah, see, plug flow is a total, when you have that kind of high velocities and the reaction is very fast at any cross section, and also please don't imagine that the diameter of the tube is 1 meter diameter. No, most of maximum diameter that is used as far as I know for plug flow is maximum 8 inches. And very commonly 3-inch tubes and 4-inch tubes are used in the industry. So that is why maintaining radial profile is very easy if the diameter of the pipe is reduced. If it is 1 inch, it is still very easy. So if it is 6 inches, okay. But no one goes even beyond 1 foot as plug flow reactors. So that is why plug flow reactor diameter is generally 3 to 4 inches where or maybe 5 and 6 inches maximum, and then you can maintain those velocities and radial mixing, infinity mixing equal to 0, all that for gas phase reactions as well as liquid phase reactions if they have very fast reaction. Fast liquid phase reactions also can be conducted in plug flow reactor.
Sir, if the Reynolds number for laminar flow is 2000 and for turbulent it is greater than 4000, and what I assume is the plug flow is more or less it is similar to laminar flow. I mean, sorry, it's turbulent flow. Since you have said that each particles, it spends the same amount of time in plug flow, could you just tell me what is the range of Reynolds number for plug flow and highlight the velocity profile of the same?
But the theoretical value for Reynolds number for ideal plug flow is infinity.
Oh.
Or that the very high flow rates only can give you even the velocity near the wall equal to some value.
Sir, it's infinity.
Infinity, that means very large velocities only have to be used to achieve ideal plug flow conditions. Otherwise you can't achieve ideal plug flow conditions. So then you may say that then what is the point? So how can you use infinity velocities? You cannot use. But when you are using almost 40,000, 50,000 Reynolds number for gas phase and liquid phase, then you can approximate that one as a plug flow reactor. You see, we assume some ideality, and if you are very near to that ideality, you may get 90% conversion. But if you don't have that kind of ideality, you will get only instead of 90%, maybe 85% conversion. And in engineering, it is approximation of perfection. So sometimes we will say that okay, with 85 I am satisfied. Or otherwise what you do is plug flow reactor length is let us say 10 meters, but you get only 85% if you assume ideal reactor. Now I will add another 2 meters to the same reactor, then in that extra length I will get my conversion. So please remember, in engineering there is no perfection. We are only approximating science so that we can run the systems, we can produce whatever we want. So that is the approximation which we have to accept. But you may ask me, sir, then why did you define ideal plug flow? Because that gives me a clear picture of what kind of thing I am expecting and how far I am deviating. Like you are imagining a very good person with all good qualities and a bad person, how far he has deviated from these ideal conditions. That is the reason why we first define the plug flow, and from there how much we have deviated, and if you have deviated 20%, 30%, how to take care of it. So that is the reason why these ideal conditions are first defined. Okay? Yeah, is it possible to carry out biochemical in PFR? Yes. Yes, because the microorganisms are so small, right? And one can theoretically, yes, PFR can be used, but the problem is biochemical reactions are very slow reactions, right? So theoretically plug flow can be used, but you should have a length of maybe 100 kilometers length, 100 kilometers length of plug flow reactor. That is why it is easy to use tank reactors. And if you look at biochemical processes, all of them are using only either mixed flow reactor, what you call chemostat, or batch reactor. The reason is it is very easy to provide that much residence time in tank reactors. But in a plug flow reactor, to maintain plug flow and then conduct the reaction, to have that to provide the residence time is very difficult because the length is very long. That's why it is a very good question. PFR can be used if the reaction time is very small, normally in minutes. And a tank reactor we can use, I think, even hours. And one of the biochemical reaction example is, this is a good question because I can answer so many things here. Wastewater treatment plant, even yesterday I was telling you about that. Why wastewater treatment plant is so big is the residence time required for reaction is very large. The reason is biochemical reaction is very slow. That is why most of the time in biochemical engineering they use either batch reactor or chemostat, which is nothing but mixed flow reactor, where you can use 8 hours, 10 hours, 20 hours residence time. Okay? Yeah. How to overcome bypass in CSTR? Okay. I think the diagram should be already there. Oh no, I removed. I think repeating. Yeah. Yeah. I have given this diagram earlier. You have mixed flow reactor something like this. We normally put from the top and then remove the liquid from the top. So this is a bad design. Instead of that, you put the input here and then remove here. So definitely bypass can be removed because this much distance at least it has to travel because of perfect mixing, right? So this is how you avoid bypass in a mixed flow reactor, right? Okay, then yeah. Same thing, yeah. I hope you understood that also.
So, you said that in plug flow reactor, both the velocity profile and resistance time is important. But these both are inversely proportional, right, sir? So while constructing a reactor, which thing we should consider? Either resistance time or velocity profile, ideal velocity profile.
No, what do you mean by inversely proportional? What is inversely proportional? Inversely proportional.
Sir, when you increase the velocity, the resistance, the resistance time of a particular molecule decreases, right?
Yeah, sure. Yeah. So to provide sufficient residence time, you have to increase the length of the reactor. That's all. That's all.
But for ideal, but to achieve an ideal velocity profile, you need to attain a certain velocity, right?
Yeah, very high velocities you have to go.
For which thing we should give importance, like either we should consider resistance time as an important aspect or velocity profile as an important aspect.
You see, to have that kind of flat velocity, both you have to consider, number one, okay? Answer to that is, both we have to consider. Number one is, first you want to maintain flat velocity profile, right? So you have to go to very high velocities, very high velocities. So next one is, you have to provide residence time. So how do you provide residence time? With that high velocity of 1 kilometer length, you use 5 kilometer length. I am just exaggerating to tell you, right? So you can, by increasing length, residence time can be increased, and by increasing velocity, your plug flow can be achieved. Increasing length. Now can you see me? Can you listen to me? Listen to me.
Yes, sir. Now I could hear you.
Okay. Now I am talking now. Okay. Okay. So now both are important. The time is important. Residence time. Plug flow velocity profile is, if there is no profile, we cannot call it as plug flow. So to achieve plug flow velocity profile, we will have very high velocity. Good. You have correctly told that when you go for high velocity, the residence time decreases because the velocity is very high. That is for a fixed length. So now I will increase my length to provide that much velocity, that time. Right? Okay. Example, if my velocity 1 kilometer is giving me 1 second, I need 5 seconds. So another 4 kilometers I will increase the length of the reactor. So that is why both plug flow as well as the residence time, both are important, both can be provided. By increasing the length, the residence time, and by increasing the velocity, the almost plug flow velocity profile. These two can be provided. Okay, thank you. Okay, yeah. I think again this is a good question. Does a reactor type selection affect the conversion? Yes. If you take batch reactor, anyway that is different than continuous reactor. If you take plug flow reactor and mixed flow reactor, for a given volume, definitely the conversion will be different. So it affects for a given volume. If you take 1 meter cubed of plug flow reactor, 1 meter cubed of mixed flow reactor, definitely you will have the difference. Yeah, the conversion generally is high for plug flow reactors. That I will tell you tomorrow why it is high and all that. Okay? Yeah. Is continuous in continuous mixed tank reactor, we may use baffles to ensure better mixing. How can we ensure better mixing in case of? Yeah, we cannot put baffles in plug flow reactors because that will disturb, that will give axial mixing and all that. So the better mixing in that too better radial mixing can be maintained in plug flow by decreasing the diameter of the pipe. If you take smaller and smaller diameter, normally the diameters used for plug flow is around 6 inches. I think 8 inches may be maximum. I don't know. I think beyond that anyone goes. So generally it is 3 to 4 inches. If you are able to reduce that 1 inch, half an inch, definitely radial mixing will be very good in plug flow reactor. That's how you have to maintain good radial mixing by reducing the diameter of the reactor, Okay. Yeah, if you have to do different reactions in same reactor simultaneously, which reactor is more efficient? You have to do different reactions in the same reactor simultaneously. No, you cannot conduct simultaneously in the same reactor different reactions, right? Yeah, we cannot. I think only one reaction at a time you can conduct, unless otherwise you have multiple reaction like A going to R going to S, series reactions, parallel reactions, they can be conducted. But two different reactions, we cannot conduct them because they may interact and there may be a problem. So I think different reactions, normally they are not conducted in one reactor at the same time, simultaneously. Yeah, this one I answered. In which reactor means plug flow is better normally. Yeah. Yeah, batch reactor is unsteady. The simple reason, because you now put the reactants in the reactor and then start the reaction. So when you start the reaction, with time, the reaction is continuously changing. The conversion is slowly increasing. So whenever there is a process which changes with time, it is unsteady state process. Unsteady state means things are changing with time. It is not steady with time. So that is the reason why in a batch reactor, the conversion changes with time. That's why it is unsteady state process. That is the very simple one. Yeah. Okay. First one. Is it possible to maintain plug flow conditions for gas? Yeah. This is quite possible. Even for gas only, it is very easy. For maintaining plug flow, gas phase is a easiest one. So I think I request all of you, anyway, thank you for so many questions. I think maybe question answer session, I think slightly better is, I think more time if you spend, that may be better. Yeah. Okay. Yeah.